Hi guys, this is Learner Beyond the Screen, and this will be my first YouTube video. So, first of all, let me establish two things. First, being that I'm still in my early but eager phase of learning, and I have a very strong desire to outsource this learning to the world. But at any point of time, if you feel like you want to question something, or if you think that I'm wrong at some place, please feel free to point it out in the comment section. I will appreciate it. And I will try to get back to you as soon as possible. And second, being that, again, this is my first YouTube video, so the quality of video or the presentation or the way I teach might not be up to the mark. So kindly adjust, and with your help, I'll be willing to improve in that area as well. So, yeah, let's begin without further ado. So, yeah, let's start off our today's topic, which is invertible bloom lookup tables. Before I jump straight to this topic, I will first take you through Bloom filters and inverse Bloom filters, their whats, their whys, their applications, and then we will jump to Invertible Bloom Lookup Tables, or IBLT in short. To understand Bloom filters, we will first take an example of Instagram sign up page where a user enters his username, let's say Tarun 1.6, and then the server will take this username and will query the database asking if there already exists a username equal to this. And let's say if it already does exist, we can simply throw a 401 else 200 saying, yeah, you can create this username, go ahead. Right, now if you will actually try to look at this query in a bigger picture and try to analyze what happened here, you will actually see that for each query the user does, the server or the instances of server will go to the database and keep asking, is this username available? Right, that's what's happening. But if you actually see, approximately 90% of queries are such queries that the username does not exist in the database already. And not to mention that if the number of usernames keep increasing, the O of n lookup will keep taking more time. And here we can actually use the concept of indexing and achieve the O of log n time. But still, this is still quite wasteful to keep asking the database, even though it has a very high probability that it does not exist at all, right? So what we do is we actually kind of, let's say for now, a simple black box that can tell us whether this key exists or not in O of 1 lookup time using probabilities. This is where data structure such as Bloom filter fits. The name might sound very scary or complicated, but it's a very simple data structure. It's nothing but just a simple array of bits. That's it. Now let me tell you how it works using an example. Suppose there are three usernames, say cat, dog, and mouse. And currently we have this Bloom array. Let me mark the positions as well. Just give me a second. 1, 2, 3, 4, 5, 6, 7, 8. Just give me 2 more. 9, 10. And initially all of these values are set to 0. Now when a username enters, we try to store it in this array, and how we do that is using k hash functions. And just so you know what a hash function is, it is simply, let's say for now, a simple black box that can take an input and produce a predictable and deterministic output. And if we change even a single character or a single characteristic of this input, the output will actually change drastically. That's what a hash function is. So let's say the cat comes, and for now our hash function produces indexes in the range of 0 to 10. Okay, and for now k is equals to 3, so for cat it produces 3 indexes: 0, 3 and 4. Now what we do is very simple, that we will go to these indexes 0, 3, 4 and set these bits as 1. That's it, and the username cat is stored here. Okay, and let's say we want to store dog as well, and dog maps to, let's say, 4, 8, 10. Now we will go to these indexes. Since 4 is already set as 1, we won't touch it, and we will go to 8 and then 10 and set these bits as 1. Great. Now when mouse comes, he wants to know that whether this username is taken or not, right? So it will go to k hash functions and will get the mapping of, let's say, 3, 4, 5. So now what it will do is it will check that is any of these indexes, does any of these indexes have a bit set as 0. It will go and check 3 already set, 4 already set, 5 not set. Then that means mouse never came. Why? Because let's say if mouse had already came, then the 5th index should have been set, right? Because if you actually remember, when I tried to set for dog, I did not do anything to the already set bit, right? So what it will do now is simply go to 3, 4 and 5, it won't do anything, and then set this index as 1 as well. Simple. And by now many of you might have noted the problem, that let's say a line comes and that guy gets hashed to 0, 8 and 10. It will go and check 0 taken, 8 already taken, 10 already taken, and then it will say, yeah, line already exists. But we know that in this Bloom filter array only cat, dog and mouse exist. So that's why it's called as a probabilistic data structure. because when it says no, this is not present, then it's 100% true. But when it says yeah, it's present, then there's a there's a we have 50-50 chance that either it was present and it said yes, or it got mapped to already set indexes and it said yes. So that's why this is a probabilistic data structure. And now another problem that you may think of is that what if all have been set to 1, right? Yeah, that could happen actually. That can happen actually. But in real world use cases, this array is very big. Like it can go up to like 1e10 or some of similar magnitude, and the probability that it can actually get filled is very low. So one of its application can be just the above username example, or something that I can think of is that if you have, let's say, multiple sharded DBs, you can have a Bloom array set in front of them, and whenever someone comes up and asks, hey, if you have this ID, instead of querying the whole database, you can simply ask, does it have? If it is no, then simply return. If it says yes, then there is a probability that it could be or it could not be. So in that case, we should be actually going into the database and actually seeing that yeah, if it's present or not. So moving on to the next topic, which is inverse Bloom filters. This is slightly different than the one we have studied above. It does have an array, but it does not consist of just bits. Let me give an example and show what it consists of and how it works. Okay, suppose you have this IBF array 0, 1, 2, 3, 4, 5, 6 and a 7, and again we have 3 usernames: cat, a dog and a mouse, and key is equals to 3. And so now what a black box or series of hash functions, along with that we also have a function which produces something called as a fingerprint, which is unique to the key. Suppose a cat produces a 59 and the indexes produced are 0, 1, 2. And now to store cat in this array, what we actually do is in these indices we store the fingerprint, that is 59, 59 and 59. And when the dog comes, suppose its fingerprint is 90 and the indices are 2, 3, 4. Then what we actually do is we see 2 is already occupied by 59, which is cat. We go ahead and erase it and then simply replace it with the 90 fingerprint. 2, 3 and then a 4. Now suppose the mouse comes and he wants to know if he is already in the Bloom lookup table or not, and let's say his fingerprint is let's say 60 and the indices are 1, 4 and a 7. So first it will go and check, like, does the fingerprint stored in the index 1 is it the same as mouse? No. Okay, cool. And what about 4? No. 7? No. Then it means that it did not exist there, or it probably did not. What if it was overwritten, right? So in order to store it, what we actually do again, 1 and then a 4, and we store 60 here. After seeing Bloom filter, you might be wondering, like, what is the use case of this, right? So instead of answering a definitive no, which our Bloom filter was doing, now we are answering a definitive yes. That yes, this element is present. Like, for example, if the mouse comes again, he can ask that this is the fingerprint, these are the indices, just go and check if anyone is there. 60, it was present. Or let's say cat, it can go and check 0, 1, 2 for the fingerprint. 59, it will go for 0, it will see yes, there was a fingerprint as 59. So yeah, this is a definitive yes. And when it will say no, there's 50-50 chance that it could have been Bloom table or it could not have been. So that's it. That's a simple explanation of inverse Bloom filters. Now we will move on to the next topic. Now the drawbacks of the above two data structures is that suppose I just give you a simple Bloom array which has some random zeros and ones and zeros and ones. Would you be able to tell or list the entries that were in it? No, right? And what if you had two Bloom arrays? Can you do some kind of a subtraction or some kind of an operation in which you could know that this following element x is in this table, but it's not in this table, right? So that's where our invertible Bloom lookup table enters. So now first I will introduce you to the data structure of IBLT, then we'll list out its operations, and then I will give you an example and show how those operations work. Okay, so IBLT is also an array, but it neither consists of some single fingerprint or a single bit. Each index of this array consists of some information, which is a count and a key sum. This is a very basic implementation of IBLT. Some advanced implementation include hash sum and some other sums also, but let's first understand the basic one. Okay, and both of these are initialized to 0. Now IBLT supports a few operations, first being our insert, then get, then delete, then list entries, so these names might suggest what their functionality would be, right? So let's just directly take an example and see how it works. Okay, let me create an IBLT array first. It will have to be slightly big. I hope my editing skills are good enough and I can make this 2x later on. For now I will denote count as C and our key sum as K. I think KS should be better, else you guys could be confused. And this time, just for simplicity, I won't be taking usernames as examples. Instead we will store integers, numbers. Okay, and if you just still want to imagine a username, let's just imagine a black box which will produce a single integer or fingerprint according to the string given. Great. Okay, so let's insert 3. Okay, so before inserting 3 into this, first we'll produce k indices using hash functions, and we'll map this out to, let's say for now k is also 3, to 3 indices. This is 0, then 1, then 2, and a 3, and a 4, and a 5. And currently our indices are 0, 3, and 5. So now what will happen is that it will go to each of these indices 0, 3, 5, and the first thing that it will do is increment the count by 1 and adding the key to this key sum 3, 1, and a 3, 1, and a 3. Right? And now let's try to store a 10 with k is equals to 3. Let's suppose we have 2, 3, and a 5. Now what will happen is it will go to 2, 3, and 5, and first it will update the 2's counter and add itself there. Then it will go to 3 and then update its counter to 2 and add, oh I'm so sorry about that, just give me a second, I wrote 2 here, it should have been 10. Great. And then this 10 will get added to this key sum, making it 13, and then this count also updates to 13. Great. So this was our insert operation. And now how get will work is that, now how the get operation works is that, let's say we want to get 3, and since hashes are probably deterministic, they will produce the same output of indices, that is 0 and a 3 and a 5. Now what it will do is check each and every one of these indices and check if any one of these guys have count double equals to 1 and the key sum equals to 3. So it will go to 0 and it will ask 1 and 3 and it will return as true. Yeah, it's there. And our delete operation, how it works is that, let's say I want to delete 3. So what it will do is that it will take all of those indices, decrement the count, and also subtract from key sum. So now the array gets updated to this state. The count goes 0 here and the key sum also goes 0 here. 0 and 3 and 5. Yeah. And first we make the count back to 1 and then we bring it down to 10. Same here. And a 10. And that's how a delete operation works. Great. And now the main operation, the main thing that actually makes it very special is the list operations. List entries operation, I'm sorry. List entries. But before that, first let's create a better or more filled IBLT array so that you can understand better. Yeah, we have our array ready, and the list operation essentially does these 4 steps. First, find any cell with count equals to 1. Now first I want to understand, like I want you to understand that if a cell has a count 1, what does it mean for its key sum? Yeah, you're right. The element inside the key sum is the element that was added to that cell only. Yes. So we store that key and then perform delete operation on that key, and then we repeat from step 1. Simple. So let's try and demonstrate these 4 steps here. Great. So, and for now, let's suppose that if there are 2 or more cells, then I will do these operations only for the cell which has the lowest index. Okay, so currently we have 0, 1 and 13, 14 and 8 indices such that their cells have count equals to 1. So we will take the earliest index, that is 0, and its key is 3. Key 3 is mapped to 0, 1 and 2. So we remove it and this reduces to 0, and this also reduces to 0. This gets reduced to 5. Now the next cell, so first let me just store this key 3 here. Now the next cell that we see is the second index cell, right? So 5 is mapped to 2, 5 and 9. This gets reduced to a 0. This gets reduced to a 4. And this gets reduced to 11. And we store our key 5 here. Now the next is this. 4. 4 is mapped to 5, 8 and 9. 0, 0, 0, 0, 1. And this will reduce to 7. And we store 4 here. Now our next cell is 9th index. And 7 is mapped to 9, 10 and 11. So this gets reduced to a 0, 0. This gets reduced to 6. This gets reduced to a 6. And again we have, oh sorry, first let me just store it here again. 7. And again we have this guy. 6 is mapped to 10, 11, 12. 0, 0, 0, 1, 8. And store it here. And again we have these 3. These gets reduced to 0 quickly. Yeah, and we have successfully listed out all the elements that were in this array. So are you able to see that if I were to give you this, just this IBLT array, and if I give you the hash function box, black box, then you'll be able to successfully list out all the elements that were in here and still have the get functionality similar to BloomFilter here also. So now let me demonstrate a quite an interesting application of this array that I actually used. So suppose you have these 2 IBLT arrays, right? Oh, let me just correct this to 1. Yeah. And currently you have 3, 4, 5, 6, 7 and 8 stored here, and we have 4, 5, 6, 7 and then 8 stored here. And now I just give you these 2 arrays. I don't give you these 2 numbers. This is our knowledge. And I ask you that which is an element that is present in array A which is not present in array B, or vice versa. So what we can actually do is a very simple operation. We can just subtract these 2 arrays. That's it. Simple. So what will happen is, for each and every index I will go and subtract the count and key sum also. So here 1 and 0, 1, and this becomes 3, 1 and a 3, this becomes 1 and then again 3, this 0, 0, this becomes 0, 0, this becomes 0, 0, this cancel out, this cancel out, this will cancel out again. So are you able to notice how I was able to narrow down a single element that was inside the array A and not in array B, and I can do this vice versa also. And even if there are multiple elements present, why can't we simply do a list entries in this new IBLT array, right? So that was another application that I found very interesting. So now we will go to the mathematical part of this data structure, and we'll be studying how to make it a successful one such that the get or list entries does not fail. Okay. Okay, so first what we will study is the what we will study is using probabilities, like if this operation can fail or not, and we will study probability failures of two functions ahead: get and list entries. So first let's start with probability that get failed. So before deep diving into the probability of the get function failing, first let's understand when would the get function fail. For a particular key A, if it's indexed to k hashed indices, then we say the get function will fail if it visits those k indices and all of those cells are non-singletons, that is having count more than 1. So that's when the get function will fail, right? So let's say the key that is being hashed is for now A, and it's hashed to particular k indices, and another key comes, let's say B, and now we want to make sure that this guy doesn't collide with A's indices. So let's define a few variables or symbols now. N being the total number of keys that are to be hashed, among which A is also there. So after A is inserted, we have n minus 1 keys. M being the number of cells, each cells of IBLT, each cell having a count and the key sum. And yeah, and let's define a random variable x, which denotes the number of collisions we have through another key to this index. So if x is 0, then there are 0 collisions. If x is 1, it's 1, then 2 and 2, so on. Probability that another key hashes and collides with any of A's indices. So what will it be? The total number of occurrences, the total number of cells, we have M, and what is the number of indices that the second key after A has to avoid? It will be k, right? Because A has been hashed to k indices. Yeah. So now if we focus on single cell, now the question becomes for every key is that, are you going to collide with me if I already have A's information with me, right? And the answer to that question will be a simple yes or no. So if we have, let's say, the leftover keys are n minus 1 keys, what we will have is essentially a sequence of y and yes and no's only. And how many trials do you have? N minus 1 keys, right? So this kind of distribution where you ask a question with a yes or no, and there are n minus 1 or n, let's say n equals to, let's say capital N equals to n minus 1, and there are n trials independent to each other. This kind of distribution is binomial distribution. And in binomial distribution, for that random variable x, we have x of I is equals to, let's say, small x. It's the formula is ncx p to the power x 1 minus p to the power n minus x. Now here, just give me a second. Yeah. Now here, n n being the number of trials, p being the probability of success. What is the probability of success? It is simply the y. Did it collide? Did this other key collide with the A's hashed indices? Did it? So as we derived above, it was simply k upon m. Yeah. And now what is the value of this small x that we desire? Is it 1? Is it 2? No. It's simply 0. Because we want 0 collisions, because we don't want anyone to collide with all of the hash indices of A, so that we can perform the get function successfully. So p of x of I is 0, then nc is 0, p to the power 0, 1 minus p to the power n, right? And if we put values, this will become 1, this will become 1, and we have ourselves 1 minus k upon m to the power n minus 1. This is the probability that n minus 1 keys do not collide with A's keys, with A's hashed indices. This is the probability. Now, by our knowledge of binomial distribution, we know that expectation of x is simply nothing but n times p, n being the number of trials, p being the probability of success, which we have n minus 1 times k by m. And since n is usually very large, we can just simply approximate this to n times k divided by m. I will be telling you about this later, but we are going to use that fact right now, that m is usually a constant times n. So we have n times k, ck, n cancels out, and we have a constant, a finite constant. So in a way, we have proved that n times p is some kind of a finite constant, and we have assumed here only that n is very large, tending to infinity, means very large. Want the p to be 0. If we add up these three conditions, then our binomial distribution tends to a Poisson distribution. And in Poisson distribution, simply we can say our probability of 0 collisions is simply e to the power minus lambda. And what's lambda? Lambda is simply the n times p that was in the binomial distribution. So we have ourselves e to the power, what was np? Yeah, n k by m. This small approximation was made by paper only, and to ease the calculation, you can go ahead and use the binomial distribution as it is also. That's fine. So what is the probability of get success, that a particular cell will still be a singleton or there will be zero collisions there, right? So let's have how and when will get fail. Excuse me. Yeah, it will fail when each and every one of those indices won't be singleton. So simply 1 minus e to the power minus nk by m is the probability that a single cell has a collision with n minus with one of those keys of n minus 1, right? And this has to fail k times independently, and that's when the get function fails. So now we'll study the probability of list function failing. List entries fail. Can you think of when will the list function fail? Yeah, it will fail when we don't have any cells that are singletons that have count equals to 1, but we still have values stuck inside the IBLT array. Yeah, you're right. The count will always have to be greater than 1 for all the leftover cells. Because what was our list entries algorithm? Find all those cells that have count equals to 1, then delete those keys, then repeat it. If we don't have any cells, we have to exit, right? So before that, I would like to show you how this also relates to a problem of hypergraph and what it is a hypergraph, and how our peeling algorithm is related to two core concept of hypergraph. So suppose A gets hashed to 1, 2, 3. B gets hashed to 3, 4 and 5. So let's draw them as nodes in a graph. 1, 2, 3, then 4, then 5. And let's have C also have hashed to 2, 5, 6. Great. Low battery. So how are we going to connect these nodes now? We can't just draw edges because A does not belong to 1 and 2 only, right? So what we create is kind of a hyper edge. Say 1 and 2 and 3 got covered by A, and then 3, 4, 5 got covered by B. Just wait a second. Got covered by B. And 2, 5 and 6 let's introduce 6 also here, and yeah, and 2, 5 and 6 are connected by C. Now what you see here is essentially a hypergraph where these cells are the nodes and our keys are hyper edges. So when will the peeling algorithm of list entries fail? It will fail when we have ourselves a 2 core. And when will a 2 core emerge? Let's take an example. 1, 2, 3, 4, 5. A hashes to 1, 2, 3. B hashes to 2, 3, 4. C hashes to 3, 4, 5. D hashes to 4, 5 and 1. So let's color them up, shall we? 1, 2, 3. 2, 3, 4, B, and C, then D. So in list entries peeling algorithm, what you essentially do is find a cell that has only one hyperedge, right? Can you spot any cell which only has one hyperedge here? No, right? That's when the peeling is failing. This is the point where our whole peeling algorithm, our list entries will stop giving us output at all, and these keys will be stuck in there. That's when we say list entries has failed. Theorem in the paper simply states that if the total number of cells that the table has, that is m, if it's greater than or equal to c of k times n, that is the number of keys, then the list entries succeeds with a probability in order of n to the power minus k plus 2. Ck is simply a hypergraph constant, and n is the keys that is being held within the table when we are doing list entries. So let's say you inserted 1000 keys, but then maybe you subtracted 2 IBLTs and you have 100 keys, then n is the 100, not 1000. Great. So in order to derive this, we won't try to see how a 2-core can be found. We will try to fix the number of vertices or edges in a 2-core. So first we'll take j. J is simply the number of keys left in the 2-core. We have already assumed that this is going to fail, and we have assumed that these are the number of keys in the 2-core because they can't be peeled. And k is simply the number of hashes, hashed indices also, or hashes you can say. So if j is the number of keys left in a 2-core and k is the number of hash indices, what are the number of endpoint of edges? So let me break it down for you. Each key touches not just at least, it touches exactly k vertices, right? So how many endpoints can there be totally? Yeah, it will be j times k. So, and now to form a 2-core, each and every vertex has to share 2 degree or 2 hyper edges, right? So what will be the maximum number of vertices that we can insert in this 2-core? There are j times k number of endpoints, and each and every vertex requires at least 2 of these endpoints, at least. So what will be the maximum of number of vertices? Yes, it will be jk times 0.5 or jk by 2. I'm going to involve some PNC concepts also. If there were m number of total cells, what is the number of ways we could have selected the jk by 2 number of vertices or cells? It will simply be m c jk by 2, right? And we also have n keys, and what is the number of ways to choose exactly j keys out of it? It will simply be n c j, right? Great. So we already had m cells or vertices, and out of which we selected jk by 2 to form our 2 core, and let's call them our candidate pool. And we already have jk endpoints that we have to arrange such that they form the 2 core. So we want these endpoints to fall on our candidate pool, right? So what is the probability that a single endpoint falls in our pool? There are total m cells and there are total number of vertices possible is jk by 2, right? This is just for single endpoint falling onto our candidate pool. So what will the probability for such jk number of endpoints? It will simply be raised to the power jk, right? Probability that a 2 core of size j forms, it will simply be mcjk by 2 times ncj times the actual probability jk by 2m to the power jk. These are simply just the number of ways and this being the probability of that forming. Yeah. So if you to actually sum this up for all j's, then we will actually get the actual probability. But as stated in the paper, in the given conditions such that m is simply greater than ck of n and number of trials being large, g is equals to 2 component in this summation dominates. That is, it's the greatest. Everything else is very small, and if we add it, it still doesn't make much contribution to the overall sum. So if we were to approximate it, we will simply put g is equals to 2 and we get ourselves mck times nc2 times k by m to the power 2k. So we will use some approximation and we'll approximate this to m to the power k and this n square. All this done to get the order of n. This is not going to be the exact probability. We already derived it right here using the summation. So the overall equation will be k to the power 2k divided by m to the power k times n square. Now since we already have this inequality, we'll use it and simply put it as ck times n. ck to the power k n to the power k n square. Now if we try to calculate the order of this, it will simply come out to be to minus k plus 2. Hence the probability of list entries failing is very low. If the k is like 4 or 5, then it's simply n to the power minus 3 or minus 2, which is very less. And now in this next section, I will implement the Bloom filters as well as inverse Bloom filter as well as IBLT in C++ program.
You said that you've been lonely, makes you cold as ice. Hard to get to know me, but better than the lies. No way I'd let you slip by. No way I'd let you say bye. You said there ain't no reason, but I'll sit here every day, waiting for the moment. trying to be patient, but running out of time. No way I'd let you slip by. No way I'd let you say bye. You said there ain't no meaning, I just wanna understand everything that I'ma pull up to the club with tequila in my cup. Pour it till I've had enough. Feel the empty in my heart. I'ma pull up to the club with tequila in my cup. Pour it till I've had enough. Feel the empty in my heart. Na 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 na. Yeah yeah. Na 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 na. Yeah yeah. I'ma pull up to the club with tequila in my cup.